Started. First of all, I have your exams for you to view. We'll do that at the end of class. All right. Remember, we've sort of started our discussion of these various experimental techniques. And so last class, we introduced IR spectroscopy. Today, we're going to talk about actually two instruments that are kind of coupled together, what's called a GCMS. All right, so a GCMS, the GC stands for gas chromatography. And the MS, that will actually dominate most of our discussion today, is the detector on this instrument, which is a mass spectrometer. All right, so let's talk about the first part of this instrument first, the gas chromatography. First of all, there are a lot of different types of chromatography out there in science. And there's this particular technique always accomplishes rather the same goal, which is the separation of components of a mixture. All right, so when you hear the word chromatography, what you want to have in your brain synonymous with chromatography is that word separation. All chromatographies are about separating these components of a mixture. So if I have a solution that has a bunch of different molecules mixed together, I put it on this instrument here and it separates them out. Each one of those components will come off at a different portion of my spectrum. All right, so chromatography, all about separation. Okay. So how does gas chromatography work? So let's take a look at a little bit of a schematics of this instrument. All right, so starting over here on the left, we have this gas tank. And just like you fill up a birthday balloon with helium. That's exactly what we have in the back, a big tank of helium. That goes through this little pressure regulator, but this is really the crux of this instrument here, this column. The gas goes through the column, round and around and around and around, and then gets to our detector on the other side. All right, these columns are like 90 feet long columns that are really, really, really thin. So what they do is they take this big long column and they wrap it up into this spool, and that's what you see pictured here. It's just a big long column that's been wrapped up, but it connects from one end to the other. All right. Importantly, this column is sitting in an oven here. Okay. This is important to how a GC works. Again, all about separation, gas chromatography. Separates compounds based on boiling points. All right, so we have a mixture of molecules. Depending on their different boiling points, that's how we're going to be able to separate them from one another in that mixture. All right? And again, our oven is kind of the key to how this is working. So what we do is we program for this instrument what we call a temperature ramp, where over time we're going to change the temperature of our oven. All right, we start out with our oven really cold, and then as time progresses, we ramp up the temperature of that oven. All right, so why are we doing that? All right, so we have our sample, right? Our mixture of compounds here. We're going to inject that onto the column. All right, well, since we're at a really low temperature when we start out with, our compound is going to be in the liquid or the solid phase, so it's just kind of stuck on that column, right? But then we're going to heat this up, and eventually we're going to pass the boiling point of that compound. All right, so it's stuck on my column, but then all of a sudden we hit its boiling point, so it's going to transition into what phase? If we boil it, now all of a sudden it's a gas. And the gas, just like our carrier gas, is going to start flowing through this column until it comes out and hits the detector. So if we have a mixture of compounds, we have this blue substance here and this green substance all mixed together, but they have different boiling points. As time goes on, first I'll hit the boiling point of that blue compound. So now it goes into the gas phase and starts traveling around my column. Hits the detector. Then eventually I'll hit the boiling point of my green compound. Now it's free and it can travel around the column and hit my detector, right? So these two used to be mixed together, but because I put them in this GC instrument, now all of a sudden they're separated out. At the end, I'm going to get this little graph where I have one peak that corresponds to that blue substance coming off and another peak that corresponds to that green substance coming off, right? So I've separated these out on that column based on time, based on their boiling point, rather. All right, now, truthfully, these columns are actually made of this special material. They've got this special coating on the inside where even if you have two compounds that have pretty similar boiling points, you can still separate them pretty effectively because of the interaction of those molecules with the coating of those columns. All right, but that's kind of a little bit more advanced. The bottom line here, at least how we can kind of crudely think about it, is we're separating these compounds based on their boiling point. All right, we inject our liquid sample onto the column. Then we heat the column. Until the boiling point of our compound. That lets it go into the gas phase and travel through the column. All right, so again, our goal is to separate out components of a mixture using this gas chromatography. It's going to do so based on boiling point. We inject our sample onto the column. We then heat up that column. Once we've reached the boiling point of that compound, it can now travel through the column to our detector. Okay? And now our detector on this instrument is a very special detector, a mass spectrometer. All right, so we're talking about GCMS. The GC is gas chromatography. This is how we're separating out our components of a mixture. All right, once they make their way through that instrument, once they're all separated out, they'll hit our detector, which is the MS portion here, a mass spectrometer. All right. Practically speaking, this is really important because let's say that we're in the lab and we're doing an experiment, right? We mix two reactants together and we form some product. Well, that reaction is never 100% efficient. We're going to have some product in there. We're also going to have some leftover reactant. We've got a mixture of things in there. If we want to analyze what's in there, we got to separate that out, right? So that's why we have this instrument here, our GCMS. It'll separate out those components of the mixture and allow us to test allow them to interact separately with our detector, our mass spectrometer. All right, and that's really what our punchline is for today. What we're going to be spending most of our time talking about is this mass spectrometry. Okay. Let's just note we talked about IR spectroscopy last time. Very similar sounding word, but ever so slightly different. Spectroscopies had to do with interactions between photons and atoms. Spectrometry is a completely different ballgame. We're not talking about light anymore. All right, what this is going to do, just simply put, is it allows us, to detect the mass of our compounds. All right, so let's take a look. So again, we have our gas chromatography instrument here. Eventually, our sample makes its way to the detector. Our detector is this special instrument, this mass spectrometer. All right, so how does that thing work? So, first of all, our sample, again, comes off the column and enters into our instrument in the gas phase. All right? We have this heating element here that keeps it in the gas phase, making sure that it's nice and hot and in the gas phase as it travels through our detector. Okay? The first most important step is once it gets into that mass spectrometer, we bombard it with a beam of electrons. Right? So those molecules pass into this detector. The first thing that we do is shoot them with a crap ton of electrons. Okay? This is really important. This induces what's called electron ionization. All right, that electron beam will knock an electron off our molecule. Okay, so we have a molecule. It's held together by these covalent bonds. Those covalent bonds are a shared pair of electrons. It turns out that if you take a covalent bond and you shoot it with a stream of electrons, those electrons will knock one of those electrons out of that covalent bond. All right, so we have our molecule. Let's just take a look at a really simple molecule here. We're going to shoot it with that beam of electrons. Okay. Initially, our covalent bond was a shared pair of electrons. But this beam of electrons knocks one of those electrons off of that covalent bond. So now I only have this single shared electron. All right, because again, that beam of electrons knocked off one of those shared electrons from my reactant side. All right, so we've dislodged one of those electrons from our molecule using this beam of electrons. Okay, now originally this molecule over here on the left-hand side, it had the same number of protons as it did electrons, so it was neutral. Over here, now that I'm one fewer electrons, what's going to be the charge on my molecule? It's going to be a positive charge, right? Now I have one fewer electrons, so I've formed this positively charged ion. What we're going to call our molecular ion. All right, so this is key to this technique. In order for this technique to work, we need our particle to be charged. So the first thing we do in our instrument is we bombard it with a crap ton of high energy electrons so that we can knock one off of our molecule, giving it this positive charge. All right? So why is that important? Then it passes through these grates that just speed everything up. The real important part of this instrument is this magnet that we're going to pass these through. All right? Now that our particles are charged, they're going to interact with this magnetic field. Right? They're going to be drawn towards the negative end of this battery and repelled by the positive end of this battery because they have that positive charge associated with them. So when they go through this magnetic field here, all of a sudden they get curved in space because of that positive charge that they have, right? Because they're charged, they're interacting with this magnetic field. It's causing their path in space to curve, okay? However, the ability of that magnetic field to curve the path of those charged molecules is going to depend on their mass, right? So over here, these particles here are our heavy particles. Their path is less curved in space. And over here, these are our very light particles. Their path is more curved in space. All right, so our positively charged particles are going to now come through our detector, but if they're really light, this magnet's going to change their trajectory quite significantly. If they're very heavy, it can't change their path very much. Okay, so then depending on the mass of those particles, how curved their path is in space, they're going to hit our detector at different points. So our very light particles will hit on this end of the detector. And our very heavy particles, they hit on this end of our detector. So depending on where on this detector a particle hits, we know what the mass of that particle is. All right? And we can really get some pretty insane resolution using this technique here, okay? So let's take a look at an example of a mass spectrum rather. Okay. On the x-axis, we have m over z, which stands for mass over charge. All right. But in organic chemistry, for small molecules, that charge is just 1, so really it corresponds to the mass of those particles. All right, our charge is always just +1. So importantly, these different peaks correspond to different particles that have different masses. All right, so our different peaks, these are particles with different masses. Okay, and we can see that this is a really sensitive technique. These differ by just one single mass unit. We have these perfectly vertical lines here. Each one represents a particle that differs just by one single mass unit, right? So the mass of one proton, one neutron, we can resolve here on this instrument, okay? Now, I sent in a sample of just methane here, but I got a bunch of different peaks out of that. So how does that work? All right. It turns out that this molecule that we create, our positively charged molecule, all right, how often have we talked about a single electron bond? Never, right? That's because why? Do we think this molecule right here is very stable or very unstable? Unstable. This thing is super pissed off, right? You just broke somebody's octet by dislodging that electron. This thing right here is inherently unstable. And so what happens is what we call fragmentation, where this thing's just going to explode into a bunch of different parts. All right, it's going to break apart specifically into a cation and what we call a free radical. A free radical is a molecule with an unpaired electron. Okay, so again, what we call our molecular ion will fragment because of that unstable, unpaired electron into a cation and what we call a free radical, a molecule that has this unpaired electron. We'll actually talk at the end of the semester about free radicals. We take advantage of them for reactions sometimes. Suffice it to say that this thing is super mad and super reactive, okay? But actually, for the purposes of what we're discussing today, mass spectrometry, this is invisible in our mass spec because it doesn't have that positive charge. What we do see is our cation. This is our visible fragment in our mass spec. Okay, so we have this process called fragmentation. Our molecular ion breaks up into multiple fragments. These are all those peaks on the mass spec. All right, so when we look at the mass spec of our methane here, we don't just see one peak corresponding to our molecular ion. We see a bunch of different peaks, which indicates a bunch of particles that have different masses. The reason that we have a bunch of particles is because that molecular ion will break up into a bunch of different parts, right? It will fragment after we kick that electron off. All right, the other thing that I want y'all to notice is how nice and neat of whole numbers we have here, right? 12, 13, 14, 15, 16, 17, nice round whole numbers that we're talking about here. If we look on our periodic table for carbon, we have this molar mass of 12.0107, right? Why do we have this fractional number here, though? Why isn't it a nice, neat number like just 12 or 13? Because this number here accounts for all the different carbons in the world, the average of all of those carbons' masses. All right, remember, there are different isotopes of carbon out there. Some of them are carbon-12, some of them are carbon-13. This mass here represents an average of those masses. All right? But when we're talking about our mass spectrometer, you have single particles hitting the detector at one time. So that means we can tell the difference between a carbon-12 atom and a carbon-13 atom in our mass spectrometer, right? That's how sensitive it is it can distinguish between those isotopes that differ by just a single proton. All right, so our masses that we use in mass spec. For carbon 12, we just use a mass of 12 AMU. We don't use its molar mass because we're not talking about a mixture of carbon 12 and carbon 13 atoms. We're talking about just those carbon 12 isotopes which have that simple mass of 12 AMU. Hydrogen, most of the hydrogen is hydrogen 1, meaning it's got a mass of 1 AMU. And most of the oxygen is oxygen 16, so we use the nice round number of 16 AMU. All right, so then if I'm going to be figuring out what my molecular ion is for this molecule here, I'm simply going to take my carbon plus my 4 hydrogens, my 12 plus my 4 times 1. That gets me to 16 AMU, or what we call in our mass spec, M over Z. All right, so this peak that we have right here at 16, this is what we call our molecular ion. We use this symbol M with a plus sign. Our molecular ion. And importantly, the molecular ion corresponds to the molar mass of your substance. All right, and this is really the punchline here of this technique. This is this big piece of information that we get. So I'm going to put it all the way back up at the top here for the punchline of mass spectrometry, right? Detect the mass of compounds. We can determine the molar mass of our compound. All right, and what we're going to show is that from that molar mass, you can determine the chemical formula. All right? Remember, just an example of a chemical formula would be like C6H12, right? So from this mass spec, what we're going to learn how to do is analyze this data to figure out our chemical formula for our molecule. All right, remember last class we talked about IR. What does IR tell you about your molecule? Functional group, right? That's what you want to have tied in your mind to IR. It tells us our functional group. Mass spec we're going to be able to use to figure out our chemical formula for our molecule. So now all of a sudden we know how many carbons there are and how many hydrogens there are. All right? And then what we'll talk about next class period, NMR, is how we get the actual shape of our molecule. Those 3 instruments taken together are how we're going to identify compounds in the lab. All right? So this step right here is for determining the chemical formula of those compounds. All right, so how do we do that? So first, let's take a look at this spectrum again. I will say that the fragmentation pattern of a molecule is unique. It's kind of like a fingerprint, all right? You can uniquely tell what a molecule is based on that fragmentation pattern. Or rather, should I say, the computer can uniquely tell what that molecule is based on that fragmentation pattern. We, as humans, unless you're going to get into really advanced mass spec, are not going to be able to look at a fragmentation pattern and be like, oh yes, that is methane. It's not going to work like that, all right? So our focus, when we get these graphs, we beeline it for the very end and look for that molecular ion, because that tells us the molar mass of our compound, which is how we'll figure out what that chemical formula is, all right? When we get more advanced down the line, maybe we'll pay attention to specific fragments, but for the most part, we ignore these fragmentation patterns. We're only really focused on that one peak, that molecular ion peak, all right? There is one more thing that we want to note here. We have our molecular ion fragment at 16. We got this little baby guy over here at 17, though. What is this thing? All right, so this is not our molecular ion peak, but what we would call our M+1 fragment. Okay, and this corresponds to the tiny amount of your compound that contains that rare carbon-13 isotope. Right? So most of the carbon in the world is carbon-12, but there is 1% of carbon that's carbon-13. That carbon-13 is kind of randomly distributed. So every 1 in 100 of these methane molecules will not contain carbon-12, but will contain carbon-13. And that's why we get a little bit of that M+1 peak over there, right? The M+1 fragment corresponds to the tiny amount of methane that actually contains that rare carbon-13 isotope. Suffice it to say that we're always going to be interested not in the very last peak, but the second to last peak, our molecular ion. All right, because again, that corresponds to the molar mass of our compound. All right, so we said that we're going to analyze this in order to get our chemical formula here. How are we going to do that? Well, let's start with another one here. All right, I'm going to tell you from the jump what this is so we can verify that we're going to get this correct chemical formula. This is what's called pentane, a 5-carbon alkane. Everybody's going to take a second, because we know how to read bond line structures, and tell me what the chemical formula is for pentane. What we got? C what? I think I already said it. C5H12. So if we analyze this mass spectrum correctly, this is the chemical formula that we should arrive at the end. All right? So this is my mass spectrum for pentane. All right? I want everybody to take a second and identify where that molecular ion is. All right? What is the M over Z of our molecular ion? Anybody got it? So I have a feeling everybody's tempted to say this big peak right here, okay? But this big peak right here is not my molecular ion. It corresponds to one of my fragments. My molecular ion is always going to be down here at this end of the spectrum. If I send in a sample of pentane, the heaviest thing that's going to hit my detector is that full molecule of pentane, right? So I'm not going to have anything larger than this hitting my detector. This peak right here corresponds to a fragment. Now it is the biggest peak. This is what we call the base peak. And it is the most stable fragment. All right, and I'm not going to say there's no information that you can get for that, but for our purposes, and especially starting out here, we're not looking at the fragments, right? Great, that's the most stable fragment. Maybe that tells you something about the structure of your molecule, but what we're after here is the molar mass, so we're after that molecular ion, right? So again, our molecular ion always lives at the highest M over Z's. We don't care about our base peak. We're not looking at our fragmentation pattern, right? The computer, that's super important information for a computer. For us, we only care about that molecular ion. All right, so again, let's look at now this portion of our graph here. What is our molecular ion going to be? Am I concerned about the very last peak? No, it's that second to last peak that I'm looking at here. This is my molecular ion at a M over Z of 72, right? So that's the molar mass of this compound. All right, so how are we going to take that information and determine our chemical formula? I just want to say, because I tend to use these interchangeably because they mean the same thing, this would be the same thing as also saying your molecular formula. They're one and the same. Okay, so how do we determine our chemical formula? We're going to use what we call the rule of 13. All right, the rule of 13 says that the mass of that molecular ion peak divided by 13 gives you the approximate number of carbons. All right, so let's test it out. Let's take our m over z of 72 and divide it by 13. All right, and we get 5.5. All right, now everybody's going to look at this number from general chemistry and be like, I know how to round stuff. We did that a ton last year, and 5.5 rounds up to 6. All right? However, there's a little bit more art than science. This isn't a hard, fast number here. This is the approximate number of carbons. So to be safe, what you always want to do is both round up and round down. Try both. All right, so we're going to round this up and say, okay, we're going to do one formula where we have 6 carbons, and then we're going to do another formula where we have 5 carbons. Okay, so from here, how do I get to my chemical formula here? How do I figure out, I know how many carbons I have. How do I figure out how many hydrogens I have? What do we know about our compound? If I totaled up the number of carbons and hydrogens, what should be the mass that I get? My fragment mass, right? Everything needs to total up to that 72 m over z. So if I know how many carbons I have, how can I figure out how many hydrogens I need? I need to add it up, right? My mass of that molecular ion fragment has to equal the number of carbons times the mass of carbon plus the number of hydrogens times the mass of hydrogen. So my 72 equals my 6 carbons times 12 plus my number of hydrogens times 1. This is my variable that I'm trying to figure out here, right? How many hydrogens do I need in order to make my mass of my compound equal to 72? All right, so first of all, if I had 6 carbons, how many hydrogens am I going to have? 0. Why 0? Because 6 times 12 is 72. So that would have to be plus 0 over here in order for this to work out. So my chemical formula with 6 carbons would be C6H0, or just C6. Is that a reasonable compound formula in organic chemistry? No. Good luck trying to draw a molecule that has 6 carbons and no hydrogens. It's not going to work out for you. All right? So this one up here, we're going to do both just to be good, but that doesn't make any sense. All right? So then instead, now you're going to figure out for me what our chemical formula would be if instead we had 5 carbons. right, so 72 equals 5 times 12 plus my number of hydrogens. 5 times 12 is 60. So how many hydrogens would I need in order for this formula to work out? I need 12. So this would be C5H12. And remember, we started this out by, just to be clear, because I take my mass of my carbons times 5, I get 60. This plus my number of hydrogens needs to add up to 72. So solving this for number of hydrogens, that's how I get 12. And we already knew this one, but notice how we were able to arrive at our molecular formula for our compound, right? So we take that molecular ion and we use our rule of 13 to figure out approximately how many carbons there are. We get that approximate number of carbons. It's this decimal. We round up and down just to be safe and get our chemical formula, figure out which one's realistic. All right. How can we tell whether a molecular formula is realistic? In that case, 0 hydrogens. That one was a little bit easy. All right. We're going to need to talk about saturated compounds. Where have we heard about saturated, unsaturated, all that jazz before? Dietary stuff. Anybody heard of saturated fats, unsaturated fats? All right, anyways. What does it mean to be a saturated compound? Saturated simply means that you have the maximum number of hydrogens possible. All right, and there are very simple formulas for saturated compounds. Okay, so the maximum number of hydrogens that you can have is going to depend on the number of carbons that you have. So let's say that you have a hydrocarbon that contains N carbons. How many hydrogens could you have? 2N plus 2. All right. So how many hydrogens in a hydrocarbon? Let's say in a saturated, how many hydrogens max in a hydrocarbon with 5 carbons? How many? So if we have 5 carbons, 5 times 2 plus 2 gives us a maximum of 12 hydrogens. So that means that if we analyzed our mass spectrum and we got a formula that was like C5H16, we know that that is not possible. That doesn't make any sense. We can't possibly have that many hydrogens. All right? So this formula here tells you about the maximum number of hydrogens you can have for a given number of carbons. If we were to put an oxygen in this as well, so talking about like an alcohol or something like that, turns out that we get the same formula, but now with an oxygen on the end. All right, but if we're talking about an amine or a nitrogen-containing compound, it's not 2N plus 2, but rather you can have a maximum of 2N plus 3 with that nitrogen. All right, so these are our saturated compound formulas. It tells us the maximum number of hydrogens that are possible for a given number of carbons. All right, if something is not saturated, we would say it has one or more degrees of unsaturation. A degree of unsaturation is for every 2 hydrogens fewer than that maximum number. That we get from our saturated formula. All right, and so for every one of your degrees of unsaturation that you have, it points to one of 2 structural features in your molecule. Means that you either have a pi bond or a ring structure. All right, so just real quickly before we move on, how many degrees of unsaturation in the compound C4H6? All right, well, what would be my saturated compound formula? C4H what? H10? Oops. So that means if I had 2 fewer hydrogens, C4H8, that would be 2 degrees of, 1 degree of unsaturation. Which means if I had C4H6, that would be 2 degrees of unsaturation. All right, so again, C4H6 has those 2 degrees of unsaturation. All right, which means that this molecule would have 2 pi bonds in there, or maybe a ring and 1 pi bond, or 2 rings. Actually, you couldn't have 2 rings with C4. But anyways, that's what those degrees of unsaturation tell you. All right, so then let's do another one here. You're going to take this spectrum, this mass spectrum, you're going to analyze it. You're going to determine the chemical formula and the number of degrees of unsaturation. That's the name of the game. All right, so looking at this graph real quick. This one's my molecular ion, right? The biggest peak up there. No, where do I look for my molecular ion? Second to the last, all the way over here, right? This is my molecular ion. Oops. This we don't really care about, but we do have a name for it. This is our M+1 peak. But this is the one that we're interested in, our molecular ion fragment. If we just want to sort of note 51, 52, 53, 54, 55, this would be an M/Z of 56 for my molecular ion. All right, so that's what you're going to take and do your rule of 13 on and determine our chemical formula. All right, so we're going to do our rule of 13, where we take that M/Z of 56, we divide it by 13, and this gives us our approximate number of carbons. We're going to do both. We're going to round up, and we're going to round down. If we round up to 5 carbons, what would be my chemical formula? Can I have 5 carbons? Why not? It's too heavy, right? What's the mass of 5 carbons? This would imply 60. Well, that can't be the case, right? My M/Z is 56, so I definitely don't have 5 carbons in this molecule. Again, not feasible. So now we'll go round down to 4. If we do our chemical formula for 4 carbons, how many hydrogens would we have on there? 8. All right, that's how we would get an M/Z of 56. Which means that we have how many degrees of unsaturation? Just 1. So 1 degree of unsaturation. All right, which again tells us about our compound here. This compound could either correspond to a 4-carbon alkene. This has a mass of 56 M/Z. Or it could be a ring structure with 5 carbons. This would also have that same mass, right? So our 1 degree of unsaturation is either a pi bond or a ring structure. Okay, so now let's pair this up All right, determine chemical formula of compounds with other functional groups. And since we're talking about functional groups, we're going to be incorporating our IR into this here. All right, so let's say I do a reaction and afterwards I take my product and I put it on my IR and I get this spectrum here. From this spectrum, what do I know is contained in this molecule? Let's do our boundaries here at 1500, 2000, 25. We got our extra one that we're going to put down at 3000. All right, we're going to ignore this first portion over here, our fingerprint region. And I see I have this giant sharp peak here in which region? My double bond region. So what does this correspond to functional group wise? A carbonyl bond, right? So now all of a sudden I know I have that carbon-oxygen double bond. All right, so now I'm going to take this compound, put it in my GCMS, and I'm going to find that I have my mass spectrum here. All right, again, we're going to pay attention to all the way at this end here where my molecular ion fragment is. And I have this molecular ion of 114 m/Z. All right, so we're still going to be able to do our rule of 13. But we're going to take the mass of that molecular ion fragment and we're going to subtract off the mass of the heteroatom before we divide by our 13 to get our approximate number of carbons. Right? Remember, by heteroatom in organic chemistry, I simply mean anything that isn't carbon or hydrogen. So in this case here, based on my IR spectrum, I don't know how many carbons I have. I don't know how many hydrogens I have, but I do know I have an oxygen in that chemical formula, right? That's what my IR spectrum told me, is that I have this carbonyl functional group. So I must have an oxygen in my molecular formula, right? So when I do my rule of 13 here, I'm going to simply take the mass of that molecular ion and subtract off the mass of that heteroatom, the mass of that oxygen. All right, and what do we take for the mass of an oxygen in mass spectrometry when we're just talking about single isotopes? Just that nice round number of 16. All right, so everybody just take a second, give me my final chemical formula for this compound. All right, so we punch this in, we get 7.5. We're going to round up to 8 carbons. If I had 8 carbons, what would my formula be? C8H 2, right? 12 times 8 plus my oxygen, which is 16, plus 2 hydrogens gets me to my 114, my total mass number. So C8H2O. And if I round down, I get 7 carbons. So my formula would be C7H14O. So neither one of these really break any rules here. All right, which one do we think is more reasonable? 8 carbons and 2 hydrogens, or 7 carbons and 14 hydrogens? This is definitely going to be more reasonable here with just 1 degree of unsaturation. All right, but when in doubt, draw an example. So try to draw a molecule that has 8 carbons and only 2 hydrogens and 1 oxygen, and you'll quickly find that that's just not possible. All right, so if you ever get a chemical formula, you get 2 somewhat reasonable chemical formulas and you can't make a judgment call, just try to draw out examples and it'll be pretty obvious. All right, and actually what we're going to find, you know, we said we're going to do both. We're going to round up and round down. Turns out that most of the time you'll end up rounding down. That's for saturated or low degrees of unsaturation, which is most of your molecules. Every once in a while you do round up if a molecule has a high degree of unsaturation. But just what you'll find is that rounding down is more reasonable most of the time. Cool. All right, and so what we did here was we used our IR information about our functional group. That told us about our heteroatom that was in our chemical formula so that we could adjust for that when we did our rule of 13. All right, so we could still get our chemical formula for our molecule using that molecular ion. We just had to subtract off the mass of that heteroatom first. All right, and again, we knew it was there because we paired it up with this other technique, this IR technique. All right, so the last thing that we're going to mention with regard to these mass spectrum is basically, long story short, not all mass specs are well behaved. All right. There are some mass spectrum that are without that molecular ion peak. Right? Our entire analysis has hinged on ignoring everything except for that molecular ion peak. Well, there are some mass specs, some compounds that are just not well behaved in a mass spec. They never actually make it to the detector as their molecular ion. They always fragment 100% of the time. So we never see a molecular ion peak. And there's one particular functional group that is notorious for having this problem. All right, and that is which functional group? Alcohols. All right, alcohols tend to almost always be poorly behaved in a mass spec. You never see a molecular ion peak. You only ever see fragments. All right, so we can get a mass spectrum here of our alcohol, but importantly, this peak over here doesn't correspond to our molecular ion. All right, so we're just going to note our IR here, as everybody noted. I'm glad that we can all pick this out. This is an alcohol. Contains that OH group. Let's say ROH. All right. So alcohols in particular usually do not have M plus peaks, molecular ion peaks. All right, and that is because they tend to undergo what's called a dehydration in that instrument, where you lose the equivalent of a water molecule from your molecular ion. Whoops. So that OH group kind of falls off, and it takes a hydrogen, another hydrogen with it. So you end up getting your molecular ion loses an equivalent of a water molecule, 2 hydrogens and an oxygen, before it makes its way through the detector. All right. Now, I sort of made the executive decision that I'll warn you when this is the case in the lab. If we do have an alcohol that's poorly behaved, I'll let you know, hey, you don't have a molecular ion in your spectrum, because it's pretty much impossible to just look at a spectrum and know whether the molecular ion is there or not. You're always going to see a bunch of peaks. How do you know whether or not this second to last one corresponds to your molecular ion? If you have a poorly behaved compound, you kind of don't. So I'll let you know, because I'll have previous knowledge of all of this, whether or not your spectrum actually contains your molecular ion. If it doesn't, and it doesn't as a result of this dehydration, not all is lost. All right, we can still figure out, oh, kind of got the punchline down there. We can kind of figure out what our molar mass of our compound is still based on this formula. All right, because this peak that we get here, this is my dehydrated alcohol, meaning that alcohol minus that water molecule. So how do I get my M plus 1 peak, M over Z? I'm going to take my dehydrated alcohol peak and do what? So not subtract it, because the water's fallen off. What am I going to do to get to my what would be the mass of my molecular ion peak? I'm going to add it back. I know that these 2 hydrogens and this 1 oxygen fell off. That's what my 78 M over Z is. So if I take that dehydrated alcohol and I add that water mass, that gets me to my molecular ion mass. Right? And what would the mass of a water molecule be? Using our nice, neat, round numbers, where hydrogen's 1 and oxygen's 16, 18, right? So in this case here, I would take my M over Z of 70 from my graph, and I would add the mass of that water molecule back to get my molecular ion fragment, my molecular ion peak mass of 88. All right, so then from here, you're going to take a second and determine the chemical formula. All right, so quickly here, I'm going to take my 88 and divide it by 13. No, why not? I got to get the oxygen out of there, right? Remember what we knew from our IR is that we have that oxygen-containing functional group. So we got to subtract off the mass of that oxygen first. So I'm going to do my 88 minus 16. All of that gets divided by 13. And this gives me that 5.5. So we're going to round up and down. Round up to 6 carbons. Round down to 5 carbons. If I did 6 carbons and I incorporated the mass of that water molecule, my chemical formula would be C6O. Is that reasonable? No. Again, got to get some hydrogens on there. So if I did my chemical formula with my 5 carbons, I would have C5H. What? So C5, that would take me to 60. I got my oxygen, which is 16. I know that everything here, plus my number of hydrogens, has to add up to 88. So how many hydrogens? 12. Is that a reasonable formula? How many degrees of unsaturation do I have here? 0, right? So if we go back to our degrees, rather to our saturated chemical formulas, just like alkanes, our alcohols have that same 2n plus 2 maximum number of hydrogens. So this would be a reasonable formula here with 0 degrees of unsaturation. Cool. All right, and then there are a few compounds that are even more poorly behaved than the alcohols, where we don't know what's going on in there, but we don't see a molecular ion peak. And for that, we're going to let the computer database do the work for us. All right, what we're going to focus on with our pencil and paper analysis of these mass spectrum are identifying your molecular ion fragment, and from there getting your mass of your compound, and from there your chemical formula.